class. Today we will discuss on the following objectives. The first objective would be to calculate the values of the principal shear planes. So the principal shear planes are those planes on which the maximum values of the shearing stresses acts. In the previous sections we have calculated the values of the principal normal stresses, but over here we are interested in calculating the values of the principal shear planes. So the principal shear planes are the planes on which the maximum values of the shearing stresses acts. So in a particular plane we can have either the values of the normal stresses or we can have the values of the shearing stresses. In the last section we have calculated the values of the maximum values of the normal stresses. In this section, we will calculate the maximum values of the shearing stresses that are acting on a particular planes. Thereafter, we will move on by the representations of the principal shear stresses and the principal shear planes, and how we can represent these principal shear stresses and the principal shear planes. Now the calculations of the principal shear planes. Again, over here again we have the oblique plane, which is represented by the triangular A, P and C. We have calculated the values of the maximum normal stresses. The maximum normal stresses are represented by sigma 1, sigma 2 and sigma 3. These are the principal normal stresses. Why? Because on these planes only the values of the normal stresses acts and no values of the shearing stresses acts on these particular planes. So on these particular planes we will not have these values. It won't be subjected to any values of the shearing stresses. So these values will be 0 in our case. One thing more, what we have assumed over here, that the directions of the normal stresses, these normal stresses sigma 1, sigma 3 and sigma 2 are in the directions of the coordinate system. So these are aligned in the directions of x, y and z. So in such a case, the values of the normal stress, the values of the sigma n that is acting on an oblique plane, which is sigma n, is given by sigma 1 L square plus sigma 2 m square plus sigma 3 n square. And in such a case, the values of the shearing stresses, the values of tau square is given by s square minus sigma n square is given by sigma 1 square L plus sigma 2 square m plus sigma 3 square n minus the whole bracket sigma 1 L square plus sigma 2 m square plus sigma 3 n square. And we know the values of the relationship between the different directions cosines, which are L square plus m square plus n square is equal to 1. So we can put the values of n square is equal to 1 minus L square minus 1 m square once in the equations, this equations. Second, we can put the values of m square is equal to 1 minus L square minus n square, and the next we can put the values one by one. Let us first, as we are interested in calculating the values of the principal shearing stresses, we need to put these values of the direction cosines in the governing equations. The governing equations are, first one is the values to calculate the normal stress, and second one is to calculate the values of the shearing stresses. As we are interested in calculating the values of the maximum values of the shearing stresses, we will put the values of the directions cosines, relationship between the directions cosines one by one in this equations. So if we put the values of n square is equal to 1 minus L square minus m square in this equations and rearranging the terms, we will get a general forms of the equations of in the forms of tau square is equal to sigma 1 square minus sigma 2 sigma 3 whole square multiplied by L square plus sigma 2 whole square minus sigma 3 whole square multiplied by M square plus sigma 3 whole square minus the whole bracket sigma 1 minus sigma 3 L square plus sigma 2 minus sigma 3 M square plus sigma 3 whole square, the whole square of this entire terms. So we have got a relationship between the various normal stresses and the principal stresses that are acting on the on this object with the relations to the shearing stresses. As we are interested in calculating the values of the principal shear planes, now we need to differentiate it with respect to L, and we need to differentiate it with respect to M. Why we are differentiating it with respect to L and M only? Because we have substituted the values of N square in terms of L square and M square. So we need, if we are interested in calculating the values of the shearing stresses, then we need to differentiate in terms of L and M. Consequently, we will put the different values of L square is equal to 1 minus M square minus M square, and again we will differentiate in terms of the different values of the directions cosine which we have. But for the time being, let us substitute the values of N square is equal to 1 minus L square minus M square in this equation. We get this formulations, and if we differentiate these values in terms with respect to L, we will get this equations. And if we differentiate again this equation with respect to M, we will get this formulations. Again we have reached the two different forms of the equation. So this one is the third equation, say, and this one is the fourth equations, and from these we will derive the values of the maximum shear stresses that are acting on the different planes we have. So we know the relationship between the direction cosines as L square plus M square plus N square is equal to 1, and we need to substitute the values of L square, M square and N square one by one, so we can have altogether three different possibilities to calculate the values of the L, M and N. So the first possibility is when L and M, when we are selecting these two values as 0, in such a case the value of N can either be plus 1 or it can be minus 1, because we know the relationship between the direction cosines as L square plus M square plus N square is equal to 1. In the second possibility can be when L is equal to 0 and M is not equal to 0. In such a case, we will get the values of M as plus minus 1 by 2 and N is equal to plus minus 1 by root under 2. The third possibilities can be when L is not equal to 0 and M is equal to 0. In such a case, we get the values of L as plus minus 1 by root under 2 and the values of N is equal to plus minus 1 by root under 2. So we are able to get the different values of the directions cosines with respect to the very different values we are substituting in these equations. So if we substitute the values of N square is equal to 1 minus L square minus M square, we will get the different values of L, M and N. The values of L will be this, so these are the values of L, M and N. In the first case, if we substitute the values of N square is equal to 1 minus L square minus M square, we will get the values of L, M and N as 0, 0 and plus minus 1. In the second case, the values would be L is equal to 0 and M would be plus minus 1 by root under 2 and N will be plus minus 1 by root under 2. And the third case would be when we will get as L is equal to plus minus 1 by root under 2, M will be 0 and N will be plus minus 1 by root under 2. So the second case would be when we are putting the values of m square in the equations of tau square, which we have shown in the previous slide, which is this equations, different values of we are putting in this equation, and correspondingly different values of L, M and N we can calculate. So in the second case, what we were discussing, we will put the values of m square is equal to 1 minus L square minus N square. In such a case, we will again get three values of L, M and N. The values of L would be 0, plus minus 1, the values of m, and the values of n will be equal to 0. The second case would be when we will get the values of L is equal to 0, m is equal to plus minus 1 by root under 2, and n would be plus minus 1 by root under 2. The third possibility would be when we will get the values of L is equal to plus minus 1 by root 2, m is equal to plus minus 1 by root 2, and n is equal to 0. So for putting the values m square is equal to 1 minus L square minus N square, we get the three relationship between the L, M and N. Now the last terms, when we substitute L square is equal to 1 minus M square minus N square, again we will get three sets of values of L, M and N. So these are the values of L. L is equal to plus minus 1, m is equal to 0 and n is equal to 0. The second case would be when L is equal to plus minus 1 by root under 2, m would be 0 and n would be plus minus 1 by root under 2. The next would be when we will get the values of L is equal to plus minus 1 by root under 2, m would be plus minus 1 by root under 2, and n would be 0. So we have all together get 9 relationships. The first is this one, second is this one, third is this one, the fourth relationship is this one, the fifth relationship is this one, the sixth relationship we have got it this, the seventh relationship we have got this value, the eighth relationship we have got it as this value, and the ninth relationship we have got this value. Now we have got the 9 suits of the values of L, M and N. Now we have to bifurcate which all values are different, and if these values are similar we will neglect all these equations. So the first one is different. All those which are shown by the red written by the red script are different. So in the second one is still different, the third one is different, fourth one is different. Now this one is a repetitions, so this one fifth one is a repetitions of the point 2, so we will neglect this one because it is mere a repetitions of the things which we have already taken. The sixth one is different. Now the seventh one is also different. Now eighth one will again neglect because this one is again the repetitions of the what we have selected in point 3, and ninth one is also we will leave it, we will neglect it because again this one is a repetitions of the sixth one. So altogether we have got six relationship between the L, M and N. Now let us summarize what we have concluded from the work which we have done by putting up the different values of n square is equal to 1 minus L square minus m square is equal to 1 minus L square minus n square, and m square is equal to 1 minus. So this one is a different thing. We have put it in the forms of n and m This one will be in the forms of L. So L square is equal to 1 minus m square minus n square. So the different possible cases what we have concluded were six different cases. So the first case is when L is equal to 0, m is equal to 0, n is equal to plus minus 1. In such a case, the maximum values of the normal stresses would be sigma 3, and no values of the shearing stress would act on that particular plane. The second case would be when L is equal to 0 and m is equal to plus minus 1 and n is equal to 0. So in such a case, the maximum values of the normal stress would be sigma 2, and no values of the shearing stresses would act on that particular planes. The case 3 would be when L is equal to plus minus 1, m is equal to 0 and n is equal to 0. So in such a case, the maximum values of the normal stress would be sigma 1, and no values of the shearing stress would act on that particular plane. So the fourth possibilities would be when L is equal to 0 and m is equal to plus minus 1 by root 2 and n is equal to plus minus 1 by root under 2. In such a case, the maximum values of the normal stresses acting on the planes would be sigma 2 plus sigma 3 by 2, and the maximum values of the shearing stresses that would be acting on that particular planes would be sigma 2 minus sigma 3 divided by 2. The fifth case would be when the values of L is equal to plus minus 1 by root 2, m is equal to 0 and n is equal to plus minus 1 by root under 2. In such a case, the values of the normal stress sigma n will be sigma 1 plus sigma 3 by 2, and the maximum values of the shearing stresses acting on that particular plane will be sigma 1 minus sigma 3 by 2. And the sixth case would be when L is equal to plus minus 1 by root 2, m is equal to plus minus 1 by root 2 and n is equal to 0. In such a case, the maximum values of the normal stresses that would be acting on the plane is sigma 1 plus sigma 2 by 2, and the maximum values of the shearing stresses that are acting on that particular plane will be sigma 1 minus sigma 2 by 2. So here we can observe that if only the normal stresses are acting, the principal normal stresses are acting, no values of shearing stresses acts on those particular planes. And if the values of the maximum values of the shearing stresses are acting, so these are the maximum values of the shearing stresses, so on those particular planes a values of the normal stresses could act on those planes. So on the planes of the maximum shearing stresses we can have the values of the normal stresses, but when we are considering the maximum values of the normal stresses acting on the plane, on those planes no values of the shearing stresses would be acting. That's why those planes are known as the principal planes, as to on those planes no values of the shearing stresses acts and only values of the normal stresses acts on those particular planes. Now the representations of the principal shearing stresses. So this is the cube which we have selected. This cube is subjected to different values of the normal stresses. The normal stresses are sigma 1, sigma 2 and sigma 3. Over here we have assumed that these are aligned in the directions of the coordinate system. So this one is represented by 1, this one is represented by 2 and this one is represented by 3. So the first case is when we are interested in calculating the values, or we are interested in representing the planes of the maximum shearing stresses. So in this case the values of the maximum shearing stresses that are acting on the plane 2 3 would be given by sigma 2 minus sigma 3 by 2, which that particular plane is inclined at an angle of 45 degree with respect to the third coordinate system which we have chosen. So on this particular plane, the maximum values of the shearing stresses that would be acting is sigma 2 minus sigma 3 by 2, and the maximum values of the normal stresses that is acting on this particular plane would be sigma 2 plus sigma 3 divided by 2. The second case is when the maximum values of the shearing stresses that are acting on the plane that is represented by 1 3 is sigma 1 minus sigma 3 divided by 2, and the maximum values of the normal stresses that are acting on the planes of the maximum shearing stresses on the plane 1 by 1 and 3 is sigma 1 plus sigma 3 divided by 2. So in such a case, the maximum values of the shearing stresses are acting over here on this plane, which is given by sigma 1 minus sigma 3 divided by 2, and the maximum values of the normal stresses that are acting on the plane, it is represented by sigma 1 plus sigma 3 divided by 2. In such a case, in order to represent it in the forms of a cuboidal, this plane has to be inclined. This cuboidal has to be inclined with respect to the angle 3 by an angle of 45 degrees. The third one would be the case when we are interested in calculating the values of the maximum values of the shearing stress on the plane 1 2. In such a case, the maximum value would be represented by sigma 1 minus sigma 2 divided by 2, and the maximum values of the normal stresses acting on that particular plane would be represented by sigma 1 plus sigma 2 divided by 2. In such a case, the planes of the maximum shearing stresses would be inclined at an angle of 45 degree with respect to the second axis. So here we can see that this cuboidal, in order to represent it in the properly illustrate it on which planes these values are acting, so it would be acting in this particular plane on the particular surfaces. So the maximum values of the shearing stresses would be this values, and the maximum values of the normal stresses that are acting on the planes of the maximum shearing stresses is represented by sigma tau 3. Sigma tau 3 is a representation which is actually represented by sigma tau on the planes 1 and 2, which is represented by sigma 1 plus sigma 2 divided by 2. So here we can conclude from these figures that if we are interested in calculating the values of principal shear stresses, then we can say that at the planes of the maximum shearing stresses, a normal stresses do exist. But in the last section, when we have derived the equations for the maximum normal stresses at those planes are known as the principal planes on which no values of the shearing stresses acts, but on the planes of the maximum shearing stresses a value of the normal stress do exists. Now the learning outcome for this session should be, we have calculated the values of the principal shear planes. So the principal shear planes are those planes on which the maximum values of the shearing stresses acts, and these are the planes on which the maximum values of the shearing stresses acts along with some values of the normal stresses do exist. Second is we have represented how the planes of the principal shear stresses actually are actually represented. So we have seen that on those planes the values of the normal stresses as well as the shearing stresses also exist, and it is inclined at an angle of 45 degree with the coordinates axis. So the planes of the maximum shearing stresses are inclined at an angle of 45 degree with the coordinates axis. So this is for this session. We will meet you in the next session. Thank you.